Okay, so my name is Sameh Gobriel. I'm based in the US. I'm with Intel Labs. And today I'll be talking about a few flow classification libraries inside DPDK and some ideas on how to extend them. And I would like very much to get your feedback if you think these ideas make sense or if you have a workload that will make use of any of these libraries. So the work presented in this slide, I'm not the only one who worked on these topics, but this work is a collaboration with a lot of my colleagues. Yipin, Ren, and Charlie are in my team in the US, and also a lot of contributions from Intel colleagues, many of whom are in the room today, Bruce, Pablo, Christian, and John. And just so you know, I live in Dublin, California, the same name as this city, not as beautiful as this one, but it is like 8,000 kilometers away. And I flew all the way from there to talk about this agenda. My talk will first go over an overview of some libraries in DPDK already there for flow classification. And I will give an overview of the hash library, the EFD, which is the elastic flow distribution, and the membership library. And the main idea here is to differentiate when to use which library and what are the features of each one. Then next, I will talk about optimization that we pushed in version 18.08 for concurrency, which will be very related to the next topic. I'm very interested in listening to the next topic. And then a few optimizations that will go into 18.11. If I leave here early, this will be posted tonight. And then some of the research directions that we are going to and how to use this library for some cloud workloads. And this is the part that I would really appreciate your feedback on. Okay, so before we dig into the details of the slides, let's take a look on flow classification, very, very high level, 10,000 feet above what is exactly flow classification. So typically, when you are classifying some incoming flows, you have a table of all the possible keys, right? Like millions or thousands of flows in a table. And then you get a packet. Out of this packet, you form a key, getting some fields out of the packet from the header and the payload. You form a key, and then you do a lookup in this huge table. The lookup might return a hit or a miss. If it returns a hit, which means you do a key byte by byte comparison with the key in the table, you retrieve the action or the value, and then do your action or know where this flow should be addressed. That's very high level what is flow classification, right? You can imagine here that keys I mean, the number of keys in the table is huge. This is the first thing that you have to remember. And also the key size can be large. If I make it to flip, okay. So just taking it one step more practical, and this is the current implementation inside the RT hash and DPDK. Typically, the key, as I was saying, the key is large. So instead of storing the full key in the hash table and do a full key comparison each time you get a comparison, this will take a lot of cycle. So to minimize the comparison cost, what you do is you get a key, then you hash it and get a signature, which is called sign here, and then you match on this signature. So you go in the flow table and do get into the bucket and match on the signatures until you find a signature match. And once you find a signature match, then you do a full key comparison to get to a hit or a miss. The idea here is instead of doing full key comparisons on all the suspects, you only match the signatures, which will be less cycles. And when there is a possible signature match, then you jump into a full key comparison. So that's basically high-level-wise what flow classification is being done inside DPDK and then also in many other network workloads. Okay, so the interesting part of the slide, which is there are few libraries, I mean, not even just these three, but there are few libraries inside DPDK, and all of them are doing some sort of flow classification. Today I'll be talking about three of them, the hash, the membership, and the AFD. And these three are all based on exact match or trying to match specific keys, not wildcards. And the idea is to know when to use which library. And if you know this guy, his name is Henry Miller. He is a very well-known American writer who lived in France most of his life. But he has a very famous saying, confusion is a word we have invented for an order which is not yet understood. So what I'm trying to establish here is to have an order or try to understand when to use each of these libraries. Basically, each one of these libraries have their own usages and applications. You can use a hash library for all the applications, but basically, when you use a different library, you will get better performance, and the other library is optimized for that specific performance. And the main differences that you have to remember across these libraries is what is inside the hash table or what is inside the flow table. The basic difference is what is in the hash table or what is in the flow table is different from one library to other, and I will cover the details in the next slide. So that's the hash library, the RT hash inside DPDK, and this is exactly what we have discussed. The hash library inside DPDK is having a flow table, and the flow table is storing signatures. I think 1 byte or 2 byte signatures. I don't remember exactly whether it's 1 byte or 2 byte. But then when there is a signature match, you jump into a key data pair. So the idea is you get a packet. The library will give you an exact match with no false positives or no false negatives, which means you are 100% sure if you get a match that this is your key. And if you get a miss, you are 100% sure that you have not seen this flow key before. So that's typically what the flow table is. With no false positives, exact match, 100%, you are absolute certain that your answer is correct. Now comes the membership library, and the main difference between this one and the previous one is in the false positives, or you are not 100% sure that you get a match. That's basically because you don't store the full key in the hash table. Before we jump into what you store in the hash table, think about the example in the upper right corner for you here. So think about this example. You have few backend servers, and you have users that are coming in trying to access these servers. And you have some sort of access control where you have a list of blacklist users or blacklist flows that should not go into accessing the backend servers. Very easily, you can have a flow table or a hash table where you are storing the blacklisted flows, and the coming flows is checked against this list, and for the bad ones, they are dropped. However, the idea of having a hash table to store blacklisted flows is okay and will work, but think about what if you store a summary, which is, we call a set summary, of this hash table. This summary will be smaller, so it will fit in the cache much easier, so you'll get much better performance, and also the lookup will be faster, so you'll get your result quicker. And the basic idea is that you drop, I mean, there are many modes for the membership library, like Bloom filters, cache distributed, and so on, but without getting into the details of the modes of the library, very high level is that you drop the full key, and all what you are storing are the signatures, and then jumping directly to the value. So you can imagine that if you get a miss in this blacklisted flow, you definitely know, if you get a miss means there is no signature match, you definitely know that your flow is not blacklisted. So all the good flows will go through very quickly, while the bad ones or the suspected ones, you have to do further analysis. So by storing just the signatures, you still can perform your classification, but at the expense of some flow, some false negatives, in that case, which says if a flow is suspected to be blacklisted, which will further require further analysis, but the good ones will go very fast. And the kind of applications that you use this kind of library are so many. Some of them, I mean, web caches is a very good example of this, of using this library. Using this library for statistics, if you to get like heavy hitters statistics, some signature matching like this one, some object indexing. I mean, a lot of usages and workloads will benefit from using this library. And if you are, I mean, I know a lot of you are also very active in the OVS community. So in the OVS, we submitted an experimental feature for the latest OVS. It's called Signature Match Cache, and it is basically using this this idea. And it gets, if you have like a lot of flow tables, it gets like 2x performance improvement. I mean, this is a work that is being done with Ericsson. And I mean, if you are interested, go and check SMC and OVS. It is an experimental feature, and check whether it will work with your workload or not. So that's the membership library. And again, the difference between this one and the previous one is whether you do full key comparison or not. The other library that is in DPDK, and we have used it in EPC, which is the Evolved Packet Core usage, is called EFD library. And this library takes it even to the extreme. It does not store anything in the flow table. So you can see here that there is no flow table at all. And what is this library doing is match action blindly. So imagine that you have this kind of use case where you have incoming flows, and you just want to distribute these flows on servers, so the subsequent packet of the same flow will go to the same server. So you have an in-order processing. If you know consistent hashing from Google, this is doing exactly the same thing, where for consistent hashing, they are doing a hash function to determine always where this flow should go. But the advantage of using a flow distributor is you are not under the mercy of the hash value. You actually can control where your flow should go. So if you want like to put all the flows that belongs to the same user on the same server, you can do that with EFD, but you cannot do that with consistent hashing. Because you are not on the mercy of a hash function. But the idea here is that you are distributing flows to destinations, and you are not storing anything in the hash table, but you given some key, you want to get the correct value. What the library is doing is it is just trying to find what is the perfect hash function that will map your key to this value. So it will go into a loop of trying all kinds of different hashes until it finds one, and will map this key to the correct value, the intended value, and then you will store this hash function for this key. So you're only storing the hash function, you're not storing any signatures or any values. So this is very compact, very concise. It will fit in the cache. It will scale to billions of flows. But the problem of this scheme, it is 100% false positive, which means if you get a flow, you will always get an answer. It will never tell you that I haven't seen this flow before. And that's the difference between a hash table or a flow table and EFD. Is you always what the flows that you are getting are always seen before. It will never tell you this packet is from a new flow that I haven't seen before. Applications that can use this library are also quite many. APC is one of them. In the labs, we have been using it to scale and the APC across servers, across many servers. Workload mapping, load balancing. Think about load balancing when you are trying to use this library. So that's the EFD. This is the membership library, and this is the hash library. Again, the main difference between the three libraries is what is stored in the flow table. One of them is storing the full key. The other one is storing just the signature. And the third one is not storing anything at all. And they differ in false positives and false negative probabilities. OK, so that's my summary of flow classification libraries in DPDK, the hash, EFD, and membership library. And then the next thing I will try to accomplish here is to talk about some optimizations that we have done for the RT hash in 1808 and also some upcoming optimization for 1811. But let me stop here for a few seconds if you have any questions about the three libraries I have discussed. OK, great. Either I am very boring, you already slept, or everything is clear. Oh, there's one question. Great.
Are there any PMDs or applications using this library currently?
So for the hash library, there are a lot of applications already using it. And you can, in the main list, there are a lot of questions about the hash library. The membership library is being used in OVS. And the EFD library, we have a POC, which is a proof of concept in the labs doing an EPC. So we are not, I'm not aware of any commercial or available application that is using the EFD as of today. But for the other two libraries, I know people are using that.
Thanks.
OK. OK, so for the DPDK RT hash and what we have done recently in 1808, so if you are familiar with the RT hash inside DPDK, it is based on cuckoo hashing, which is this cute, nice bird up there. And the basic idea of cuckoo hashing is for every key that to be inserted in the hash table, it gets two locations, two possible locations in the hash table. So for a key F, for example, it can get into either a primary location or a secondary location. Both of them are available, so it goes to its primary one. For a different key, G here, both of its locations are occupied. So what will happen is G will push a key out of its location. This key will push another one out. And this will go on until an empty location is found and all the keys are inserted in the hash table. So that's basically the idea of cuckoo hashing, and it comes, the white gets its name is because of the cuckoo bird, which pushes another birds out of their nests. So the idea here is keys are pushing everything around until all the keys settle in their primary or secondary location. And this is the kind of performance for the table utilizations that you will get when using cuckoo hashing. If you are only using one hash function, you expect out of 1 million key inserts, you expect only to insert 38% of the keys. If you are doing two hash functions without displacement, without moving keys around, you expect to get around 75% of the keys inserted out of 1 million. And we're using the cuckoo hash, which is the RT hash inside DPDK, you can get around 98% of all your keys inserted in the table. And Please remember the 98% because we'll get back to it in a little bit. But that's the basic idea of the RT hash. There is no new invention here. Just trying to put keys in the hash table and move keys around so you can insert as many keys as possible in the hash table. So this has been in DPDK for many versions now. And what we have done in 1808 is read-write concurrency, to add read-write concurrency for the hash table. So read-write concurrency means that while you are writing in the table, while you are inserting flows in the table, you can still simultaneously read your keys out. You don't have to stop the reads, you don't have to stop the lookups until your writes have finished. So think about a pass that a key is inserted in the table, and it has to push another key, and the other key has to push, so on. So you can have a very long insertion pass or keys moving around in the table until you finally inserted your key. So if you think about concurrency, I mean, keys, when you are looking up keys in the table, the keys have to be in their final location before you do a lookup. So before, what we added for 1808, what typically you will be doing is that when you are inserting, you will stop all lookups. All lookups have to be stopped. You finish the insertions, and then you allow for lookups to proceed. That's before 1808. For 1808, we allowed for, or we implemented concurrency, read-write concurrency, which means instead of locking, which is using coarse-grained locks for the library and preventing all the lookups from going on, we used TSX, which is an Intel hardware feature, Intel transactional memory, which basically what it is doing, it is having fine-grained locks implemented in hardware. These locks are implemented in hardware, and they are monitoring each cache line. So if a cache line, if two writers are writing into a same cache line, or a writer is writing in a cache line and the reader is reading it, it will detect this conflict and will roll back execution. This is done transparently, and this is all done in hardware. So we use this feature in the hardware, which monitors the cache lines and will detect data conflicts. And when a conflict is detected, the execution is rolled back. And this is the kind of result we get when we apply the 1808 batch with TSX for the RT hash. So the x-axis is the number of cores, reading and writing. The red line is the traditional way of doing things, which is with big locks. And the green line is with using this patch. And as you can see, the speed up, the normalized speed up, I mean, it scales nicely with the number of cores reading and writing in the hash table. So the next topic, the next presentation will specifically talk about this problem, and I think they have a solution that does not have any locks. That's why I'm very interested in the next talk. But that's basically what is already released in 1808. For 1811, which I think I will be able to submit this patch tonight. The idea is, I told you to remember the 98% number, which is this one. So although cuckoo hashing or the RT hash implementation provide very good table utilization, you can insert almost all your keys. There is still a possibility of, there is 2% probability that you will not be able to insert a key, which is 98%. So this is okay with most of the applications, but for some applications, this is not okay. I mean, for example, for a telco application, they need to insert all the keys, 100% of the keys. They cannot tolerate 2% keys not inserted. So, so the idea here is we will post a patch to add extended table to the RT hash, which means that you can insert your keys using the regular cuckoo hash in either in the primary or the secondary location. But if you fail to insert, and if there are too many keys being pushed around until the maximum pass length, what you will do is that you will extend your hash table with extended bucket, which is just a linked list, and the key will go into this linked list. For 2% of the time, the key will be there, and for the rest of the time, it will either be in the primary or the secondary location. So this will avoid dropping keys, and also will avoid resizing the hash table during runtime, which post solutions will not be acceptable for a workload like a telco workload that needs 100% of the keys be inserted, and they don't need any interruption of lookups and insertion while you are resizing your hash table. So this will handle all the insertion failures, and you can. Please take a look on the mail list, and if you think if you have any feedback on this idea or any review on it, or it will not work with your workload, let us know. Okay, so I finished almost all the things I wanted to talk to you about, which is an overview of the libraries, the optimizations that we have pushed in 1808, and the extended table idea that we are targeting 1811. So for the rest of the slides, I will be talking about cloud workloads and using membership library in the cloud workloads. We have just started looking into that. If you think this idea doesn't really make any sense to you, just shoot it now before we do any kind of work. If you are also, if you have something that will benefit from this research, let us know. So cloud workloads and KV stores, big data. These are all names for the same thing. But the basic idea about KV stores in many of the products already there, whether it is Google Bigtable or Cassandra or Couchbase or Amazon Web Server, is they use what they call log structured merge trees or LSM trees. And basically, these are huge stores for KV stores, key value stores. Basically, what the LSM trees are doing, they have an in-memory store for KV and several stores offline or on the disk. Whenever there is a write, you write both into the memory store and also to the commit log in disks, which is supposed to be fast. And then from time to time, because you want your in-memory store to be fast, you are pushing updates to the disk. So on the disks, you will have many versions of the same KV stores, C1, C2, and C3. And whenever you are reading or looking up, you are looking up all of them to get the match. And over time, you are trying to merge the ones in the hard disk or the disk to form a new tree. So this is high level, very, very high level, what LSM trees are. And the benefit of LSM trees, it fits or it sits somewhere between. It has an acceptable performance for both reads and writes. So that's a crash course on LSM trees. So why does this have anything to do? Okay, why does this have anything to do with the membership library? The basic idea is the membership library is just a store that will tell you where the keys are. So you can think of using the Bloom filters in the membership library to determine whether an object is in the mem table or any of the versions on the disk. This library is very well optimized to run on platform and will do the lookup very quickly. And also we are thinking, because range queries is very important for this kind of KV stores, which means I get a key, do I have this key in any of the ranges I'm looking for? We are thinking of extending the membership library to support range queries, which means answer range queries, which is not supported today. So these are the two things that we are looking to use the membership library in. And if anybody is interested in pursuing these ideas further, I mean, please let me know. This will be an interesting direction for us. So as a summary of my talk, we had an overview of the flow classification in DPDK. Please try all the libraries in DPDK, and if you have a workload that will benefit using one of them, make use of it. Don't always go to the hash table. For certain network workloads, the membership library and the FD will make sense. There are optimizations for read-write concurrency pushed in 1808, and we are working on extended table for 1811. Please review the patch and point out if there is any gap in the RT hash that will not fit your workload. And for the last thing, if you have any comments on the research direction for KV store, please let us know. I'm looking for collaboration or developers who are interested in that. And that's it.